So when you were reading chapter 2 in your textbook, you should have had kind of an eye-opening experience in terms of that is very different type of data, this categorical data, than what we took our test on earlier, or last week, right? So I'd like to kind of talk about, in general terms, we're going to make kind of a little organizer here. Sometimes we call them graphic organizer. And we're going to organize the information about the two different types of data. We have so far already learned about last week and the weeks before quantitative data. And then what you read about over the weekend was called qualitative data. And they are different kinds of data. So all I'm thinking about in terms of this graphic organizer is things that they may or may not have in common, and then things that they're definitely different. They mostly have differences, not a whole lot that they share. So I want us to think about, it could be something that we already know. It could be something completely different, something that you read about. I would write this down if I were you. All the different things that are different and the same about these two different kinds. Okay? There we go. So give me something you know about one of these things. So I'd like everybody to participate in this conversation at some point. So give me one thing, Josh, about quantitative quality. It could be about graphs. It could be about the kind of data they are. It could be about anything, really. If you have anything you want to add. Okay, it's numerical data is another way to describe quantitative data. It is numerical, very good. Anybody want to add to that? Not just numbers, but specifically, Matt? It's subjective? Objective. What do you mean by that? I'm looking for a different word, that's all. Mathematically, we don't use objective, subjective. We're going to use something else. Samantha? Measuring, measurement, continuous maybe is a way to think about it. So I would agree with you that it is continuous, measuring, measured, measurable. When I say continuous, I mean like the salaries, right? They're continuous. They are 2,376,273.37 cents or something. It's measurable, okay? Whereas qualitative is not necessarily measurable. It's not numerical. It does have numbers to it, but we call that categorical, okay? Sometimes we talk about it being counts. We are going to count the number of blue-eyed people in the classroom later. We're going to count the number of sophomores in the school. We're going to count. There are these categories. Okay? Give me some other things that we know. What kind of graphical displays are in either or? Do they both of them have graphical displays? Pie chart, okay? So which one of those, is it quantitative or qualitative for a pie chart? Qualitative is going to use pie charts, I agree. Now, they both do use graphical displays, so I'm going to go ahead and just write graphs. Now, there are different kinds of graphs, but they both can be displayed in terms of a graph. What are some others that you've read about, the qualitative graphs, besides pie charts? Give me another one. Ayana, give me a different kind of graph that you read about. It could be a graph we've already used. Give me any kind of graph. A bar graph. Is that qualitative or quantitative with the bar graph? It's actually qualitative, okay? Bar charts is what I think they use, is the word bar chart is the language that they use in the book, I believe. But bar charts are categories. They're going to show categories. When you think about a bar chart and qualitative or categorical data, do the bars touch each other? They do not, okay? They're separate bars. Now, because we're talking about the categories, they have green eyes. This is the number of people that have blue eyes. Okay, this is the number. I'm using that example because that was what your homework was on. But It could be lots of different categories. It could be categories for a grade in the class. It could be category of any kind of categorical data there. What kind of a graph looks like a bar chart, but it's actually a quantitative or measurable, Cameron? A histogram. Now, on a histogram, what is true about the bars? They do touch. They're continuous. If the bars don't touch, there's some sort of gap in the data, okay? But that's kind of one of the differences. And then obviously the horizontal axis would be labeled differently as well. Give me some. Contingency table, exactly. And we're going to use those a lot today. Is that qualitative or quantitative? Qualitative, very good. A contingency table. And I'm not sure if the book calls it this, but they can be called a two-way table as well. Did they say that word at all? No? Okay. So that is something you should know, because I'll go back and forth. Two-way table. We'll look at those in a little bit more detail in a few minutes. But yes, definitely contingency tables. Any other graphical displays that we may have already studied or that you learned about when you read? There's one in the classroom that we've been kind of adding to every day. A dot plot. Good. Dot plots measure, is it qualitative or quantitative? Quantitative. So we know a dot plot. Give me another quantitative data display. I'm sorry? We haven't really talked about line graphs at all. And there's kind of a reason we don't really study those, but line plots, I think they call them. They do exist, I agree. We can put them on here. Nothing we've necessarily studied in detail. Katie? Stem and leaf plot, we call those just plain old stem plots in this class, but we have in the past, back in middle school, they were called stem and leaves. Very good. Anything else? Box and whisker, and then again, we call them just box plots here in statistics. I'm not sure why. Is it just kind of like, are we just shortening the names? I'm not really sure, but yes, box and whisker plot. Anything else? I think that might be all that we did with quantitative. That sounds about right. Anything else about qualitative? I have two things I'd like to put out there. Anything called a marginal distribution? Does that word sound interesting, or something that you read about? We're going to actually find those today, figure out what the heck they are. And in the same kind of breath, we have a conditional distribution. Both of these two things can deal with percents. The marginal and conditional distributions are often given as percentages. So those are definitely qualitative type things. What kind of percents did we deal with last unit? We dealt with percents at all. The frequencies, very good. The cumulative frequency or relative frequencies, I agree. So they both can deal with percents to some degree, but more often than not, percents we do think about as qualitative data. The percent of people that have green eyes, or the percent of people that have, that are wearing flip-flops in the class, or that kind of thing. Qualitative categorical data. Okay? Good. So we know the difference between the two. Here's an example of a bar chart. This is an example you should have read about. Oh, I know one thing I wanted to add. In the example from your textbook with qualitative data, that Titanic example, we're going to look at that a little bit more detail today. But what is this thing that they were talking about with the area principle? Anyone want to explain what they meant by the area principle? What is meant by that? If you remember, the example in the book was like the bigger boat versus the littler boat with the graphs, and they related that to the area principle. What is meant by that? Katie?
It was something like the amount of people in the ship, like it makes it look like it's bigger, but it's really not.
Right. Yeah. So your area on your graph should really represent the percentages that we're talking about. When we think about a pie graph, we really want that the area that is cut out of the slice of pie to represent authentically the variable that you're representing. So that is something that if you are unfamiliar with that term, you should go back and look at that again. Okay? All right, so that's something you should look up. Good. So let's look at this bar graph here, or bar chart, either way. It does represent the count in a particular category. What is this particular bar graph or bar chart or whatever missing? The title, right? So we definitely want to always include a title. What could an example of a title be in this particular case? Because we always want to make sure that it's in context. So probably, rather than write the word title, we should make the title in context. What could a title be? Lexi, what do you think? Based on what you read about and what you see here in the graph. How about frequency? So the number of people in each class, right? So number of people in each class. There are two things, and we should say on the Titanic, right? Because we know that we're going to make it specific. There are two clues when you look at this particular graphical display that tells me it's a bar chart. There's two things you should be looking for. Give me one of the two things. The bars aren't touching. Good. Give me something else that tells me it's a bar chart and not a histogram. One of the values, and which value is that? Which axis, horizontal or vertical? So this horizontal axis is in terms of what kind of a variable? But it's either qualitative or quantitative. Which one? Qualitative data. So this is categories or qualitative data. And so if it was a histogram, it'd be measure, right? Okay, it'd be something like units would be dollars or whatever, different units. Good. Pie charts are something that you looked at as well, okay? We look at pie charts here. Again, we're missing titles. And again, we should be looking at the area that's represented by each piece, and we're actually going to be creating a pie chart today. Should represent the different things. I'm not a huge fan of the three-dimensional pie chart. I know that like Excel does them and things like that. I really, if you're going to do a pie chart, which you're going to do for me today, I really want to make sure that you're including the counts and sometimes even the percentages. Or a lot of times, actually, I probably prefer percentages than counts. And we're going to do the degrees when you do it for me later. So we have to figure out how many degree angle and that kind of thing. What variable is being measured here? Or not measured. What variable is being represented here? The classes, right? So that would be our title. Okay, it would be the classes of people on the Titanic. Oftentimes, a pie chart has one variable that it represents, and this particular one would be the classes of people on the Titanic. That's just the one variable that's being talked about. When we talk about pie charts, or actually any charts, but pie charts are very easy to see, there are several things that are wrong with this picture. Don't yell them out. I want you to look at it. And I want us to think about some things that are inaccurate or wrong. And don't say because it's a 3D pie chart. I'm not a big fan of those, but that's not what's wrong with it. Okay, that is absolutely 100% correct. One of the things is that the percentages don't add up to 100. Why should they? Because we're filling in a whole pie, right? If it's going to add up to 100, actually, if you add these up, what do you notice? It's over 100, okay? So the percentages don't add up to 100. It's over 100. Can you think maybe, in the context of the problem, why that might happen? Elena? There you go. So if you have categories that are going to overlap, like in this case, and why might the categories overlap, do you think? Think about context here. These are some dangerous behaviors. People are heavily drinking, using alcohol, or using marijuana. Why might they overlap? Why might it make sense that they would overlap? Catherine? Because they're probably not independent events. okay? Meaning that if you use marijuana, it's probably more likely that you'll use alcohol as well. And we call those independent. So that's a situation we're going to talk about in a little bit. But yeah, they don't add up to 100. It's very likely impossible that the categories are going to overlap, and that's one of the reasons, okay? So I might say that here. Categories overlap. I see another issue. Matt? Exactly. The one that really jumps out at me is a 50%, right? 50%, if you know 50%, you know that means half, right? So what should the area principle, it should be half. Don't you agree? Okay? So the percentages don't match the slices of pie. Is that okay to say it that way? Match the slices. I'll say areas of the slices. Good? Do you notice anything? Those are the two things that jumped out at me. Do you guys notice anything different? You mean both of these are the same category? It's hard to distinguish between the two. I would agree with you. Okay? Does that mean they've ever used it? Does that mean that they use it every weekend? How do you define that? I agree. They're not clear, distinct categories. Catherine? That actually doesn't bother me. Okay? That's a good thought, though. I mean, I agree. Like, a lot of times those labels are inside it because the lines are drawn. That's okay. We are missing what? Well, is that a title, maybe? Yeah, maybe that's a title. But, yeah. I'm looking, just kind of jumping. Those are the only two things I could think of, but maybe you come up with more. You sure? I think that's all I could come up with in terms of what was odd or unusual. But you'll see some of these type of questions again.
When did you put the actual data? So and so people out, so many people?
Okay, and that is something, as a math teacher, I prefer when you talk about percentages, showing me how you got the percentage, and we're going to look at that in a couple minutes with the contingency table. But that's a great idea, but it's not required in a pie chart. Okay? Okay. Let's talk about contingency tables, though. Okay? Again, they're sometimes called two-way tables. Okay? I more often than not will call them a contingency table, though. And if you notice, it is a relationship between two variables. In the pie chart and the bar chart that we've done up to this point, how many variables were we measuring at once? In the pie chart that we just looked at with the heavy drinking, use of marijuana, whatever, it was just one thing we were measuring, right? The not criminal behavior, what did I call it? I call it the bad behaviors or whatever I said, dangerous behaviors. That was the variable that was being measured. When we talk about some of the other, the Titanic, we were talking about the classes of people. That was the one thing of the kind of classes of tickets that were bought on the Titanic. Okay? So that's something that one variable was being measured. In a contingency table, there will always be two variables. So here's an example of a contingency table, and it's something that you probably looked at a little bit when you did your reading. And I want us to decide what the two variables are. Okay, so let's start with the alive or dead. Rather than say alive or dead, because those are parts of that's like they call those the factors. But what's the actual variable? No, that's a different one. I'm talking about alive or dead. How do I just generalize that, Matt? Survival. Did they survive? Did they make it? Okay? Don't give me the answers to the questions, but just tell me in general what is that variable. So I agree. I think survival is a great way to say that. So we're going to call this the survival category. They either are alive or dead. I agree, Zachary. And then how about the other variable that's being measured? Gender. Good. Because you are either alive, you're either a male or you're a female. Okay? So the two variables that are being measured is the gender and whether or not you survived the Titanic disaster. Two different variables, and they relate to each other. It's a way to organize the information. Anytime that we have a contingency table, you do want to always make sure that you have included the totals. Okay? The totals for both the rows and the totals for the columns. What distribution uses these totals? You have a choice, either the marginal or the conditional. The margin, it's actually the marginal. And it helps me remember because it's in the margins of the table. Okay? So these are the numbers that we're going to use for our marginal distribution. Okay? Let's create a marginal distribution with this information for gender. So anytime I ask you to do this, you're going to just kind of get this out of the way, so then leave it over there maybe. How would I do that? A marginal distribution of gender. Well, that is the question. That is the question. I want you to create it. Here's my table. What do I do? Perfect. We have two different, if we look at gender, it says of gender. So we know we're going to look at our genders. So we're going to be looking at the totals of the genders. And we're going to say, okay, for males, and you need to say whether it's males or females. I don't know if you're familiar with these symbols for male and female. It's a science thing. If you've seen it before, if not, that's okay. But we have males and we have females. And so we're going to say, I think the first one was males, right? Yep. So I have what numbers divided by what numbers? The total of males, which is 1,731, divided by, you're always going to divide, when you're talking about marginal distributions, you're going to divide by, I call it the total. It's the total of the totals. Just my shorthand. So what is that? Divide that. You guys have calculators. Change it to a percent for me. What is that as a percent? Looks like a little over half. Double checker. Did you get 78.6? Never round to a whole percent here. I think a good rule of thumb is the tenths place, 1 decimal point. You got what? Yeah, 78.6, right, that's exactly right. So 78.6%. I always want to see what you divided by, okay? So you need to include both of these. Okay, how about for females? What number divided by what number here? 470 out of 2,201. And when I divide those, I should get 21.4. Because these percentages should add up to 100%, shouldn't they? But you round the next one up. When you round up the next, right, it should round up to 4. Okay? So we have our marginal distribution of gender. Okay? So let's look at what a conditional distribution would be. By the way, I could do the same thing for marginal distribution of survival. And wouldn't that be the alive would be 711 out of 2,201, and dead would be 1490 out of 2,201. You could do the same thing for the other variable as well. We're just going to do gender right now. What does a conditional distribution look like? So let's figure out the difference. What would a conditional distribution be like? Well, a marginal distribution, we're only working in the margins. A conditional distribution of gender for, we'll say of gender, and we'll say alive or dead, it's fine. Conditional distribution of gender. Well, we have two we could choose. We could be alive or we could be dead, okay? So let's stick with the alive. Notice where I'm at in my table. I'm no longer in the margins. Conditional distributions work from the inside of the table, but what you're going to divide by is what you're looking at. In this case, we're going to divide by the gender totals. We'll divide by the female total and the male total. So we're going to look at the alive. This is just one. There's how many conditional distributions for gender could we have? Alive or dead, right? So we're just going to do one at a time. We'll stick with just the alive. So for alive, we could have male, and we could have female. And let's look at those percents. So what percents am I looking at? What am I dividing by? What divided by what? 367 divided by? Down here. You're looking at the gender, right? It did say of gender, so you're going to be dividing by your gender total. Okay? So 367 divided by 1731. Tell me what that number is. 21.2%. Okay? And then let's go ahead and look at the other one. It'd be 344 divided by 470. What percent is that? 78.8? Is that what you guys got? Did you get 21.2 over here?
Well, it's 0.7319.
73.2? Okay. They just don't add up to be 100%. Something's wrong. Can I just see your calculator? Did I divide them right? Did I make sure I'm doing it right? 367 and, oh, I know why. Never mind. That's okay. These aren't going to add up to 100 necessarily. Okay. All right, this is fine. So my question becomes now, so based on this, we can answer the question, is gender independent, we'll say the other way around, is survival independent of gender? And the information I have provided right above this question will answer it. So this is if you're going to write anything down, this is what you write down today. How do I answer this question? Because I guarantee it's going to come up again. 100% guaranteed. Is survival independent of gender? And I have everything up on this page answers it. It's a yes or no question. Tell me what you think. What am I comparing to be able to answer that question? The percentages that correspond to each other. So I'm going to look at the percentage of all males on the ship. There was 78% of that ship was males. 78.6% of the ship's population was male. But how many people survived that were male? Of the survivors were male. 21%. And then we look at the females. 21.4% of the ship population was females. But of the people that survived, how many was females? So we are comparing, when we compare apples to apples, we are going to be comparing this percentage to this percentage. And then we're also going to compare this percentage to this percentage. Should they be close to each other? These are definitely not close to each other. Do you agree? Since they're not close to each other, we can firmly make a conclusion. They are not independent. They are very, very dependent. Okay? So if the percentages are far apart, like they are here, they are dependent on each other. And we'll reason through and see why that makes sense. We're going to say that they are dependent. We should be specific. We should go ahead and use our context. Survival appears to be dependent of gender because, and let's use our statistics, because what? The marginal distribution of gender is very different from the the conditional distribution of gender for those that survived. Does that make sense? Say, use those words. So because the marginal distribution, and you'll have those numbers up there, is very different from the conditional. I would even go as far as comparing and saying 21.2 is not equal to 78.6%, and that 21.4 is not equal to 73.2. Make sure you're knowing what you're comparing. We're comparing boys to boys and girls to girls. It's very important that we're clear about what we're comparing. Question? Yes. So I know that what you're comparing. Make sure that, because what if you compared 73.2 to, whoa, what over here? You know, the other ones are kind of close, like 73 and 78 is not too far. Like, I need to know that you know what you're comparing. Okay? Question, sweetie? I think I moved something here. It says, survival appears to be dependent on gender because the marginal distribution is very different from the conditional distribution. And then you showed me what you compared. If the percentages are close to each other, they're pretty independent. If they're really far apart like they are here, they're dependent. Now, what's close? What's close? What would you consider close? How close is close? Is 20 and 30 close? I don't think that's close enough. 20 and 25? Definitely under 10. Okay? This is where you kind of get into the shades of I'm not sure. You know what I mean? Like, it has to be under 10. Okay? But could they be as far as 6 or 7% off, but the other ones are like 1 and 2? That's where you can say, well, the evidence suggests that. It's possible that. It's likely that. Okay? So we're not going to say for certain. This one was very clear. They're very far apart. Okay? That's why I use this example. But sometimes they're not always this far apart. Okay? So you have to kind of use your own judgment here. But absolutely, Esmeralda, less than 10. Okay? Good. Any other questions about this problem? Could you go back and look at your number 7 now and answer it differently on your homework? I think I'd like to do that. Oh, before we get to that, though, can you explain why you think, just in the context of what you know about the Titanic, what you know about the Titanic? Byron. Hello. Why does this make sense? Why is one dependent than the other? Or why is one dependent on the other? Cameron has her hand up. Yeah, you watch the movie? The women and children got on the boats, right? The men didn't get on the boats. So it makes sense that more women survive than men. I agree with you. Why percentage-wise were there so many more men on the boat, though? Yeah, the workers, the people that worked on the boat were mostly men. Okay? So that does make sense. Even though there was definitely more men on the boat, the percentage of women was much higher that survived. Okay? So contextually, I agree with what this evidence is showing. Okay? It's very clear that they are definitely dependent because, as Cameron said, they put the women and children on the boat. Okay? Good. Very good. So let's go ahead and look at your homework, if you would. Okay? Well, actually, we're going to look at homework in a minute. Sorry. One more thing we got to do. We're going to go ahead and take a blank piece of paper out for me. We're going to do a little exercise similar to your homework. Yes, love? I do. It's all blinged out and everything. Because everyone needs a little sparkle in their life. Okay? So we're going to do a little survey in this class, collect some data, some actual data, some real life situation, and we're going to count, because that's what categorical data does, it counts the number of males and females. So I'm going to count myself in this, so we're going to do boys first. And you're going to have to, by the way, write this down on your paper. You're going to make 2 different pie charts, and you're going to use a contingency table to do it. And this is something you're going to turn in for like a participation grade today. Yes, I want you to draw the contingency table on your paper. You'll do 2 pie charts. They can be on the back, one can be on the front, one can be on the back, but it is something you will physically turn in to me today. Okay? So how many males do we have? 1, 2, 3, 4, 5, 6, 7, 8. 8 boys. There's only 5 boys in my first block class. Do I scare boys? Is AP statistics scary for boys? Boys just don't like math? No, that's not true. I think it's Ms. Macker, it scares them off. That's all right. Okay, a little bit. It's all right. It's good. I don't mind being afraid. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 female. Oh, 19 including myself. 19 females. So we have 27 people in the class. That's our total. We now have to ask, according to my contingency table, the other variable. We had gender. What's the other variable that we're measuring here? Eye color. So I want you to identify with one of these eye colors. I have one of those eye colors. It depends on what I'm wearing, and depends on whether I'm crying or if it's like cold outside. I call, so my eyes go from gray to blue to green. If you are like that weird gray to blue to green eye color, you're an other. Okay, that's me. I'm an other if your eye color changes. Look at me, I'll tell you what you are today. You are definitely brown today. Okay, so let's start with males only. How many males do we have that have green eyes? Raise your hand. 1. How many males do we have that have blue eyes? 1. Brown eyes? 1, 2, 3, 4, 5. So none of them. Oh, 1. Who's Hazel? Oh, Byron's sleeping is what it is. I think Byron has brown eyes. Byron. Wake up, baby. Come on. All right, females, how many of you have green eyes? Raise your hand high. 1. They actually say that green-eyed people are more intelligent than anybody else, so just so you know. There's statistics that prove it. I don't know. All right, blue-eyed females, any of you out there? 1. Brown-eyed females, put your hands up high. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And that should mean that we have 4 of us that are changers. 1, 2, 3, 4. That's true. Okay. So let's go ahead and use this contingency table. I'm going to pause the recording briefly. I am going to ask that you come up and get a compass and a protractor. We're literally going to construct a pie graph today. So you will need, I'm going to put this on the empty table in the back so we're not kind of in these poor people's desk area. You need 1 protractor and 1 compass. Please do not draw the circle without knowing where your center is. So I'm actually going to do it this way. I'm going to start by creating a dot on my paper that I know for a fact that's where the center of my circle will be. So go ahead and start with a dot on your paper. Then take the sharp part of the compass, place it on the dot, open up your compass to a radius that will fit on your paper, and literally just draw your circle. Okay? So the extra leads leave in the compass, please. So you have a compass that creates the circle. That's the only reason you'll need your compass. And then you're going to have the protractor. We need to create a marginal distribution to be able to graph it. You could also graph a conditional distribution if you wanted, but you just have to make sure that you're labeling it appropriately. We're going to do marginals here. I want us to create a marginal of eye color. Actually, why don't we do it this way? I did it differently in my second block class, but why don't we actually graph the results that we found? Well, we'll do this. I know what we're going to do. We're going to graph a marginal distribution of eye color, and we're going to do a conditional distribution of eye color for the second one. for, let's do females. There's more females because the males, there's so few of them. Maybe they're not as representative, okay? So we'll do the conditional of eye color for females. So we're going to do, those are going to be our two graphical displays that we're going to create. So this is one pie chart, this is second pie chart. Are we okay with that? And honestly, these, if they are independent of each other, shouldn't the breakdowns be very similar? Right? Okay, so let's see if they are. So we're going to start by creating a marginal distribution of eye color. So let's start with number 1. Okay? So marginal distribution, if you remember, we're going to have to find percentages. We're doing eye color here. So we're looking at this margin here, because that's the eye color margin. So we'll obviously have to do some counting. We have 2 green-eyed people in the class. We have 2 blue-eyed people in the class, 19 brown-eyed, and 4 of us eye-changing colors. Okay? If I want to do a marginal distribution of eye color, we're going to say green, blue, brown, hazel, or other. We'll just say other. And you're going to tell me what you divide by and find a percent. So, what's the green? 2 divided by what? 27. Very good. I'm going to find the percent for that. What percentage of people in our whole class? 7.4%. I'm going to leave it as 0.70. Is it 0.074, right? Sorry. 0.074. I'm going to leave it that way. I'm not going to convert it to a percentage. That's okay. You can leave it as a decimal. And the reason I'm leaving it as a decimal is because I want to use that decimal to help us figure out how many degrees in our pie chart we should make for the green-eyed people. Okay? So, how do I figure out how many green-eyed people there should be? Well, if you use your calculator, I'm going to need my calculator here. I think I found my calculator. Good. Where are you, calculator? And I'm going to say 0.074, or I'm going to go ahead and just leave it as, what was it, 2 divided by 27? It just got moved. 2 divided by 27. It didn't clear it. 2 divided by, there we go, 27. Just so I'm not rounding, okay? And what am I going to do to figure out the number of degrees I want? Matthew? Where'd you get 360? Yeah. We're going to fill up our pie chart. They should add to 100%. So how many degrees make up a circle? 360. So we're going to multiply this by 360, and we're going to get about 26.67 degrees. Okay? So I want you to show me that. So we're going to say about 26.7 degrees. Make sure you have units and you don't have to show me what you multiplied by, but you're telling me the degree measures. How do I draw 26.7 degrees on my pie chart? Well, first thing we probably need to do is to have some place to start. I don't care, draw some radius somewhere in the circle. I'm going to draw this radius here. Okay, so start by drawing a radius in your circle. Could be anywhere, doesn't matter. And right now, first of all, how many slices of pie should we have? 4. Okay. We're going to start by drawing the first slice of pie. And I'm going to take my protractor and I'm going to line it up with the line that the radius that I drew on my circle. You're going to have to rotate your picture somewhere. All of your protractors have little holes in the bottom. That's what should go over the center of your circle. And then you should line up the radius that we drew on the circle with the protractor itself. Now my question becomes, where is 26.7 degrees? Am I going to be using the inside numbers or the outside numbers? The way that I've drawn it here, it's going to be the inside numbers. because I'm treating it as this, and I'm opening it up from the left to the right to the left, the way I've started drawing here. So I'm going to go around to, this would be 10 degrees, 20 degrees. I'm saying 21, 2, 3, 4, 5, 6, 7. I'm about right there. Did you see that? Again, look at your thing. On the inside, we're going 10, 20. Maybe it will let me do that. Wouldn't this be great? So it's about there, 26.7 degrees. And so I want you to do that. Notice I made a little mark on the outside of my protractor. I can physically count where that would be right about here. And then I'm going to move my protractor out of the way, and I'm literally just going to draw. Now, obviously, I don't want to go all the way out to here. I'm just going to go to the circle itself. And this will be green. My green-eyed people in this classroom, this is the marginal distribution of eye color, so you should label it as such. And then you'll need to go and you'll just continue on. You'll now use the line we just created, and you'll move your protractor. I'll do that in just a second. Hang on, I'll go back in just a minute. I'm going to take my protractor, maybe, and I'm going to line it up this time here. It's a little skewed because of the way that the dimensions are working on the computer, but the screen. But 20, and then I'm going to have to figure out what color is next. What color did we do next? I think we did blue. Okay, blue's the same, isn't it? The same count. So blue is also 2 out of 27, which is about 0.074 or 26.7 degrees. And we'll go, notice how I've lined up my protractor this time. And I'm just going to continue around the circle to fill in all the pieces of the pie. There should be 4 total, right? Brown's going to be kind of hard because brown is more than half. So I might do blue, because blue, I'm sorry, hazel or other. Because if you look, 19 out of 27 is brown. That's bigger than our protractor. So do the blue instead. And then whatever's left over will be the brown. Okay? Any questions? So you're going to do the marginal, and then you're going to do the same thing for conditional. You're going to do a conditional distribution of eye color. We said for the females, and then you'll graph that. She had a question first. What was your question, baby? Oh, just to see it. Okay, good. Yes. Because I took 0.074 and I multiplied it by 360. Because it's 7% of the whole circle. Okay? All right. So I'm going to pause the recording again. I want you guys to work on this. When you're finished, I want you to go ahead and turn it in to me. I'll take it. You can just hand it to me. It's supposed to go in this third little inbox because that's your inbox for 6th period. Can y'all just do that? Just throw it right in here in this inbox, right here in the 6-block inbox. And I'm going to put up your answers to your homework up here, okay? So you can check that. We'll go over that a little bit more clearly when you're finished, okay? So here are the answers to the homework, but I don't think that these answers are enough. So I think we need to talk about what other pieces of information am I missing from these that I would like to see from you. So if you look at number 1, what % of females are brown-eyed? How'd you get that? What numbers divided by what numbers? Okay. No, and so notice here's something I want you to show me what you divided by to get that number. Keywords here, whatever follows the word of, is normally what you divide by. So what % of the females, so we're going to look at the total of our females, which is 32, and we want in that female row, how many of them had brown eyes? That's 16 out of 32. Okay? So in other words, we were looking at 16 brown-eyed females divided by the total number of females. Any questions of where those numbers came from? Okay? So Second question, what percent of brown-eyed students, so now what am I dividing by? What am I dividing by? 36, because there are 36 brown-eyed students. And we're looking for females of those brown-eyed students, so that would be 16 out of 36. Okay? Again, show me what you're dividing by. What percentage of students are, so now we're talking about what percentage of students, so what am I dividing by here? 64. It's the total of all the students. Which ones of those are brown-eyed females? That would be, again, 16, but what we divided by changed every time. What follows the word of identifies what you divide by. Okay? The distribution of eye color. Notice I have the percents there, but I really want you to show me what the percentage was. So it doesn't say the word marginal distribution, but isn't that what we're doing? Okay, so I really think if I were you, I would want to see that word marginal there. It bothered me that it wasn't there, but I'm telling you it should have been. So blue would be what out of what? Blue would be 10 divided by 64. Brown would be 36 out of 64. And the other would be 18 out of 24. Oh, sorry, 64. Thank you. All right. And then we look at the conditional distribution of eye color for the males. We're going to say 6 divided by of the males, 6 divided by 32. Is that 18.8%? Double check me. What's 6 divided by 32? Y'all have calculators. I'm not a human one. Tell me what it is. So it's 18.8 is right? Okay, good. All right, brown would be what divided by what? 20 divided by 32. And then the other of the males is 6 divided by 32. Now, in order to be able to compare them and answer question 7, because question 7 said, is gender independent of eye color? What am I comparing to answer that question? Well, remember, we're comparing apples to apples. So we're going to compare the blue percentages to the blue percentages, the brown percentage to the brown percentages, and the other percentages to the others. Are they close enough? So is 15.6 close to 18.8? That maybe. 56 and 62. It's a little far off for me. And then 28 and 18, that's almost 10%. So what are we going to say to that? No. Okay? So to me, I think the percentages are too far apart. If the percentages are not close to each other, what do we say? They're dependent. They have to be close to each other in order for them to be independent. And so that's the answer to number 7. But you had to show me what you're comparing and why. So here's what I would answer to number 7. They have to be close to be independent. I would say 15.6 does not equal 18.8. 56.3 does not equal 62.5. And that last one was 28 point. Those are okay, but this last one definitely not. It should be 18.8. Therefore, because they are not close enough, we're going to say that eye color, we should say something like this. There is evidence to suggest. This is the evidence. There is evidence to suggest that eye color is dependent on gender. Okay? Any questions about that? Good? All right. So here's your homework. we need to talk about what this first part for a minute. I'll go back to the homework in a minute if you want, the one from last time. Notice it says 1 or 2 or 3 or 4. In your homework, the first 4 problems ask you to go out and find a pie graph, a bar graph, a contingency table, or whatever. So you can search the internet, but you need to physically print and bring it to me. Or you can copy and send it to me in an email. That's okay. We can bring it up and show it on the smartboard. But I want you to find, you can cut it out of a magazine, you can cut it out of a newspaper, you can go online, but I want you to find one of the graphs. And it depends on whether you did 1, 2, 3, or 4. It could be a bar graph, a contingency table, pie chart. I'm not sure what the other options are. Okay? I don't want you to make one. I want you to find one that already exists. Okay? And then the rest of them are just problems I want you to answer. Okay? All right.